I was listening to music the other day, and it just made me stop and think. When sound moves through a solid material, like a guitar string vibrating, we hear a wave. But what's actually moving the energy at the atomic level? What is the fundamental particle of sound? So that's what we're digging into today, this really mind-bending concept called a phonon, the quantum unit of vibration itself.
It's a fascinating idea, and the definition is key here. A phonon is what we call a quasi-particle.
Well, quasi-particle.
Right. So think of it less like a permanent particle, like an electron, and more like an organized disturbance, a synchronized ripple moving through this huge lattice of atoms.
Okay, so it's an event more than an object.
Exactly. They are basically quantized sound waves. It's a really useful analogy to think of them like photons, which are, quantized light waves.
That makes sense. It grounds the idea immediately. And the name, phonon, I read it, comes from the Greek word phonon.
It does, yeah. It means sound or voice. It was suggested, I think, way back in 1930 by Yakov Frenkel.
So these tiny packets of vibrational energy, how do they actually affect the materials we use every single day? What's their role?
Oh, they're absolutely crucial. I mean, in condensed matter physics, their movement is energy transfer. Phonons are what fundamentally dictate a material's thermal conductivity.
How well it conducts heat?
Precisely. And its electrical conductivity, too. If you can control how phonons move, you can essentially control energy efficiency in everything from a computer chip to, say, the insulation in your windows.
Okay, let's unpack that a little. In crystals, the way atoms are arranged means they can wiggle in different ways. I know there are two main types of phonons we should talk about.
That's right. For any crystal that has more than one atom in its smallest repeating unit, you get two main branches of vibration. First, you have acoustic phonons.
Acoustic, so related to sound.
Exactly. These are these coherent, low-frequency vibrations where all the adjacent atoms are moving together in sync, in phase.
And I see these LA and TA acronyms. That's longitudinal and transverse.
Yep, you've got it. Longitudinal acoustic, or LA, is where the atoms vibrate parallel to the wave's direction. Think of pushing a slinky. Transverse acoustic, or TA, is when they vibrate perpendicular, like a wave on a rope.
Okay, so that's the first type. What's the second?
The second one is where things get really interesting. Optical phonons. These are high energy, and the key thing is they are out-of-phase movements.
Out of phase, so they move.
Against each other. Instead of swinging together, adjacent atoms swing against each other.
Wait, hold on a second. Why are they called optical? That seems like a huge leap to go from sound to light.
It's an excellent question, and it's because of the powerful connection it reveals. In ionic crystals like table salt, for example, this back-and-forth counter movement actually creates an electrical polarization, a tiny little dipole moment.
And that means?
That means these specific vibrations can be excited by infrared radiation. They are infrared active, that's the link. You have a mechanical vibration that's interacting with the electromagnetic spectrum.
That is wild. That shift from a purely mechanical thing to something that interacts with light and electricity, that feels like it brings us right to the edge of modern research. And, speaking of tackling these kinds of complex systems, whether they're physical or digital, it always requires real expertise. This deep dive is sponsored by Embersilk. If you need help with AI training, automation, or even just uncovering where agents could make the most impact for your business, you should check out embersilk.com for your AI needs. All right, so let's look at that cutting edge. What are researchers discovering now about the potential of controlling these sound particles?
There's a ton of optimism in the field right now. One of the huge discoveries is something called phonon tunneling.
Tunneling, like quantum tunneling.
Exactly like that.
Wow.
Research has shown that heat can actually flow across tiny, tiny gaps, we're talking nanometers, through the quantum tunneling of phonons. This completely defies classical physics.
And what does that mean for us practically?
Well, think about microelectronics. You have all these tiny components packed together generating heat. Even if you separate them with a vacuum gap, this shows heat can still jump across. It's crucial for designing next-generation cooling systems.
And what about superconductivity? I've heard phonons are involved there too.
Absolutely. In conventional superconductors, the glue that binds electrons together into Cooper pairs is often the exchange of phonons.
And we know this for sure.
We have very strong evidence from the isotope effect. If you swap out atoms in a material for their heavier isotopes, the mass changes, right? That changes the vibrational frequency, the phonons, and that directly affects the superconducting temperature. It's a smoking gun.
Okay, now let's get to the wildest prediction I've read about. The idea that phonons could have something like negative mass. or even negative gravity. That sounds impossible.
It sounds like science fiction, I know. But the prediction is rooted in physics. So, phonons are predicted to travel faster in denser materials. So, theorists predict that as a phonon approaches a gravitational source, where the material might be slightly compressed and denser, it would actually speed up and deflect away from the source, not towards it.
So it would behave like it's being repelled by gravity.
In a way, yes. It mimics an object that has negative gravitational mass.
Yeah.
The effect would be incredibly small, but the implications are staggering.
So what does this all mean? I mean, the fact that a particle of sound might have properties related to anti-gravity is just astonishing.
Yeah.
And then you see that in 2019, researchers managed to isolate individual phonons without destroying them for the very first time.
A massive breakthrough. That level of control is unprecedented.
Exactly. So if we can now isolate and manipulate the quantum unit of sound, imagine applying that control to thermal management or even that negative gravity effect we just talked about. We could be on the verge of learning to manipulate energy and matter in ways that could just change everything. If you enjoyed this deep dive into the weird world of quasi-particles, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.